Now that you know how to load and save data in Octave, put your data into matrices and so on, in this video I'd like to show you how to do computational operations on data. And later on we'll be using these sorts of computational operations to implement our learning algorithms. Let's get started. Here's my Octave window. Let me just quickly initialize some variables to use for our example. So set A to be a 3x2 matrix, and set B to a 3x2 matrix, and let's set C to a 2x2 matrix, like so. Now, let's say I want to multiply two of my matrices. So let's say I want to compute A times C. I just type A times C. So it's a 3x2 matrix times a 2x2 matrix. This gives me this 3x2 matrix. You can also do element-wise operations and do A dot times B. And what this will do is it'll take each element of A and multiply it by the corresponding element of B. So that's A, that's B, that's A dot times B. So for example, the first element gives 1 times 11, which gives 11. The second element gives 2 times 12, which gives 24, and so on. So this is the element-wise multiplication of two matrices. And in general, the period is usually used to denote element-wise operations in Octave. So here's the matrix A, and if I do A dot caret 2, this gives me the element-wise squaring of A. So, 1 squared is 1, 2 squared is 4, and so on. Let's set V to a vector. Let's set V as 1, 2, 3 as a column vector. You can also do 1 dot over V to do the element-wise reciprocal of V. So this gives me 1 over 1, 1 over 2, and 1 over 3. And this works too for matrices. So 1 dot over A gives me that element-wise inverse of A. Once again, the period here gives us a clue that this is an element-wise operation. You can also do things like log V. This is an element-wise logarithm of the V. E to the V is base E exponentiation of V's elements. So this is E squared E cubed because this was V. I can also do abs V to take the element-wise absolute value of V. So here, V was all positive, but we did abs, say -1, 2, -3. The element-wise absolute value gives me back these non-negative values. And negative V gives me the minus of V. This is the same as -1 times V, but usually you just write negative V instead of -1 times V. And what else can you do? Here's another neat trick. So let's see. Let's say I want to take V and increment each of its elements by 1. Well, one way to do it is by constructing a 3x1 vector that's all 1s and adding that to V. So if I do that, this increments V from 1 to 3 to 2, 3, 4. The way I did that was length of V is 3. So 1s, length of V by 1, this is 1s of 3 by 1. So that's 1s 3 by 1 on the right. And what I did was V plus 1s 3 by 1, which is adding this vector of all 1s to V. And so this increments V by 1. And another simpler way to do it is actually to type V plus 1, right? So here's V, and V plus 1 also means to add 1 element-wise to each of my elements of V. Now, let's talk about more operations. So here's my matrix A. If you want to write A transpose, the way to do that is to write A prime. That's the apostrophe symbol. It's the left quote. So on your keyboard, you probably have a left quote and a right quote. So this is this is actually the standard quotation mark. Is let me type A transpose. This gives me the transpose of my matrix A. And of course, A transpose. If I transpose that again, then I should get back my matrix A. Some more useful functions. Let's say lowercase a is 1, 15 to 0.5. So it's a 1 by 4 matrix. Let's say I set val equals max of a. This returns the maximum value of a, which in this case is 15. And I can do val int max a, and this returns val and int, which are going to be the maximum value of a, which is 15, as well as the index. So it's the element number 2 of a that was 15. So int is my index into this. Just as a warning, if you do max A, where A is a matrix, what this does is this actually does the column-wise maximum. But say a little bit more about this in a second. Still using this example of the variable lowercase a, if I do a less than 3, this does the element-wise operation, element-wise comparison. So the first element of a is less than 3, so it gives 1. Second element of a is not less than 3, so this value says 0, because it's false. The third and fourth elements of a are, less than 3. Third and fourth elements are less than 3, so this gives 1, 1. So this does the element-wise comparison of all 4 elements of the variable lowercase a to 3, and it returns true or false depending on whether or not it's less than 3. Now, if I do find a less than 3, this will tell me which are the elements of a, the variable a that are less than 3. And in this case, the first, third, and fourth elements are less than 3. For my next example, let me set a to be equal to magic 3. The magic function returns, let's type help magic. The magic function returns functions called returns these matrices called magic squares. They have this mathematical property that all of their rows and columns and diagonals sum up to the same thing. So it's not actually useful for machine learning as far as I know, but I'm just using this as a convenient way to generate a 3 by 3 matrix. And these magic squares have the property that each row, each column, and the diagonals all add up to the same thing. So it's kind of a mathematical construct. I use this magic function only when I'm doing demos or when I'm teaching octave like this, and I don't actually use it for any useful machine learning application. But let's see, if I type RC equals find a greater than or equals 7, this finds all the elements of a that are greater than or equal to 7, and so RC sends a row and column. So the 1, 1 element is greater than 7, the 3, 2 element is greater than 7, and the 2, 3 element is greater than 7. So let's see, the 2, 3 element, for example, is A2, 3, is 7, is this element out here, and that is indeed greater than or equal to 7. By the way, I actually don't even memorize myself what these find functions do and what all of these things do myself. And whenever I use the find function, sometimes I forget myself exactly what it does. And I type help find to look up the document. Okay, just 2 more things I'm going to quickly show you. One is the sum function. So here's my a, and then type sum a. This adds up all the elements of a. And if I want to multiply them together, I type prod a. Prod stands for product, and this returns the product of these 4 elements of a. Floor a rounds down these elements of a, so 0.5 gets rounded down to 0, and seal or ceiling a gets rounded up, so 0.5 rounded up to the nearest integer, so 0.5 gets rounded up to 1. You can also let's see, let me type rand3. This generates a 3 by 3 matrix. If I type max rand3, what this does is it takes the element-wise maximum of 2 random 3 by 3 matrices. So you notice all of these numbers tend to be a bit on the large side because each of these is actually the max of a randomly element-wise max of 2 randomly generated matrices. This is my magic number. This was my magic square 3 by 3a. Let's say I type max a, and then this weird open close square brackets comma 1. What this does is this takes the column-wise maximum. So the max in the first column is 8, max in the second column is 9, the max in the third column is 7. This 1 means to take the max along the first dimension of a. In contrast, if I were to type max a, this funny notation 2, then this takes the per row maximum. So the max of the first row is 8, max of the second row is 7, max of the third row is 9, and so this allows you to take maxes either per row or per column. And if you want to, and remember it defaults to a column-wise element. So if you want to find the maximum element in the entire matrix A, you can type max of A, like so, which is 9, or you can turn A into a vector and type max of A colon like so, and this treats this as a vector and takes the max element of that vector. Finally, let's set A to be a 9 by 9 magic square. So remember, the magic square has this property that every column and every row sums to the same thing, and also the diagonal. So here's a 9 by 9 magic square. So let me do sum A1. So this does a per column sum. So I'm going to take each column of A and add them up. And this, lets us verify that indeed for a 9 by 9 magic square, every column adds up to 369, adds up to the same thing. Now let's do the row-wise sum. So the sum A, comma 2, and this sums up each row of A, and indeed each row of A also sums up to 369. Now let's sum the diagonal elements of A and make sure that that also sums up to the same thing. So what I'm going to do is construct a 9 by 9 identity matrix, that's I9, and I'm going to take A and construct, multiply A elements-wise. So here's my matrix A. I'm going to do A dot times I9, and what this will do is take the element-wise product of these two matrices, and so this should wipe out everything in A except for the diagonal entries. And now I'm going to do sum of A of that, and this gives me the sum of these diagonal elements, and indeed it is 369. You can sum up the other diagonal as well. So instead of top left to bottom right, you can sum up the opposite diagonal from bottom left to top right. The commands for this is somewhat more cryptic. You don't really need to know this. I'm just showing you this in case any of you are curious. But let's see. Flip UD stands for flip up down. But if you do that, that turns out to sum up the elements in the opposites of the other diagonal of A, and that also sums up to 369. Here, let me show you. Whereas I9 is this matrix, flip up down of I9, takes the identity matrix and flips it vertically, so you end up with, flip UD, end up with ones on this opposite diagonal as well. Just one last command, and then that's it, and then that'll be it for this video. Let's set A to be the 3 by 3 magic square again. If you want to invert a matrix, you type pinf A. This is technically called the pseudo inverse, but it doesn't matter. Just think of it as basically the inverse of A, and that's the inverse of A. And so I can set, temp equals pinf of A, and if I take temp times A, this is indeed the identity matrix with essentially ones on the diagonals and zeros on the off diagonals up to a numerical round off. So that's it for how to do different computational operations on the data and matrices. After running a learning algorithm, often one of the most useful things is to be able to look at your results, or to plot or visualize your results. And in the next video, I'm going to very quickly show you how, again, with 1 or 2 lines of code, using Octave, you can quickly visualize your data or plot your data and use that to better understand what your learning algorithms are doing.